So thanks for the brief introduction, PK. Again, my name is Parker Vascik, and I'm going to spend the next couple of minutes talking to you about what MIT has been conducting roughly the past year and a half, to look specifically at the implementation of potential urban air mobility systems in US cities, in an attempt to identify what the leading operational constraints will be for these networks, to understand how these constraints may limit either the initial implementation of these networks or the scale up as we seek to put more and more vehicles into the sky. I'm going to wait for my slides to come up. But again, the goal of my presentation is specifically in the theme of this panel to discuss air traffic control scalability and try to provide a framework for how to think about this problem and perhaps to help people in this room identify some of the opportunities, either in the technology space or the operations space, to begin addressing this particular challenge. So MIT's, if I can click the slides. You can click them for me, please. MIT's approach to this research over the past year and a half has been to conduct a series of exploratory case studies in 3 major US cities, specifically Los Angeles, Boston, and Dallas. We selected these cities because they were perceived by potential operators as near-term, high-value markets for these types of services. And also from our side as academics, they have very different features and requirements they would place upon both the vehicles themselves in terms of range, payload capabilities, and operating environment, as well as the system and how the network would operate. So through a 4-step process, we first identified promising potential markets within these cities to identify where near-term services may be provided by a UAM system. Based upon these markets, we then defined a series of 10 to 12 reference missions within each city. And these reference missions captured a variety of, again, requirements that may be placed upon these types of operations. So we could evaluate the operation of the system in different conditions. We applied a very high-level notional concept of operations for these various reference missions we defined that looked both at ground operations and must be conducted by passengers and ground crews, as well as air operations for flight crews in the vehicles themselves. By doing a day-in-the-life analysis for each of those 32 reference missions we did among the 3 cities, we began to see a variety of operational challenges emerge that could either limit the implementation or the operation of that route, or actually limit or bottleneck the number of vehicles that could operate on that specific reference mission. To provide you some image of the networks we were looking at, I'm presenting here our reference missions in Boston and Los Angeles. You can see that a majority of the missions that we defined were focused right around the urban core centers, relatively short range to points of demand within the city centers. But again, to add some variability to our study, we also reviewed a variety of longer range missions, perhaps beyond the ranges that Uber at least has highlighted in their concept of operations, that went to outlying city centers, potential recreational areas, and mega commuting communities. Now, by looking through the 32 reference missions that we evaluated, we began to see that there were some challenges that emerged, operational challenges, that were relatively ubiquitous, that appeared in all of the reference missions, or a majority of them. We also identified a set of challenges that didn't appear in all of them, but rather tied to specific environmental features of a city or a specific characteristic of a certain type of operation or consumer group. By evaluating, again, these specific, more ubiquitous challenges, we defined this set of 7 operational constraints that we perceived as most likely to impact the implementation or scale-up of an urban air mobility network. Now, by focusing on the probability or how likely they were to occur in the various cities and reference missions, and the level of impact or the level of bottleneck they may create for the operation of a network, we really identified these first 4 as the prioritized constraints that have the highest system-level risk we were interested in investigating further. I think what's interesting is the 4th one on this list, this safety and certification of electric aircraft operations. That's one of the constraints that obviously appears now. It doesn't depend upon the scalability of the network. It's more of an implementation constraint. I'm looking forward to the conversations that I think we're going to hear from Tom and Greg later today about vehicle certification standards, and hopefully some of the operations certification that has to be done as well. But we were most interested in MIT in these first 3 constraints, which you can think of as scalability constraints for an urban air mobility network. For example, if we talk about air traffic control with the theme of our panel, air traffic control is not necessarily going to be a major bottleneck at the beginning of these operations. We frequently fly charter helicopters and general aviation aircraft supported by the current air traffic control system within our cities today. But as operators, Uber and other operators, intend to operate more and more vehicles at higher densities within our cities, we expect this constraint to to become binding very quickly. Our initial analysis, again in Boston, looking at Sao Paulo operations, identified that the current air traffic control staffing and structure can usually only support about 5 to 10 simultaneous operations over a city, which again is a major bottleneck that quickly comes on. And I think that Uma will be able to talk about her experience more in Sao Paulo over our panel. So at MIT, we wanted to understand and do a little more analysis into what actually were these constraints and what drove them. So this is how we framed it at a high level. We wanted to understand how these 3 scalability constraints in red boxes at the bottom actually impacted the throughput capacity of an urban air mobility network. And we dissected that throughput capacity, which you can think of as the number of vehicles per infrastructure point at a time or on a specific route at a time, into these 4 potential bottleneck points. Starting on the right, we obviously have those related most to ground infrastructure. You have the ground access capacity, or how can you actually move people in and out of the aircraft infrastructure for that first and last mile transportation. You have the terminal capacity, which is how many passengers can your terminal support for the operations that must be done within the terminal. You have the airfield capacity, which you can think of as the number of gates that can really support the passengers loading and unloading, as well as the airfield side in terms of the surface transportation movements and runway operations. And finally, the airspace capacity. How many aircraft can you move through a sector? How many aircraft can air traffic control handle? And how many aircraft can the procedures for the various infrastructure points support? So focusing specifically on air traffic control, we identified what we thought were the 3 key mechanisms that really define or set that airspace capacity as well as those procedures capacity into airports. The first one is the fundamental design of your airspace and route, how we lay out our controlled airspaces and potentially our exempted areas for operations, and the routes that we use depending upon wind and weather conditions. The second one is the separation standards that are used by air traffic control within controlled airspaces. Obviously, they're highly dependent upon weather, but also other factors such as CNS capabilities control these standards. And then thirdly, and perhaps most importantly from our analysis, we identified was really the controller and pilot workload, another fundamental mechanism that limits the sector capacity of an airspace. Another way to view this is through an influence diagram, where we can think of really those first 2 mechanisms, the airspace and route design and the separation standards, as fundamental structural factors that we create as an industry to control airspace that really set the theoretical throughput of an airspace sector. These are either codified in regulations, they're typically long-term projects that are defined and cannot be changed necessarily in a short time period. The other mechanism acts as a human factors one that depends upon controller staffing, the training, decision support tools that allows a sector to actually reach that theoretical limit set by the structural factors. At MIT, we wanted to go a level deeper with this to understand what specific technologies could be invested in, perhaps to change these mechanisms and work through them to increase a sector's capacity, or what concept of operations could also be created to do that same effect. And we disaggregated one more level, as you can see in this diagram. And these orange boxes really represent areas of potential research that can be done by this community to potentially increase the throughput capacity from an air traffic control standpoint. As an example, if we look at communications, navigation, surveillance, the CNS capability, developments in that area, whether they be technologies, decision support, or concept of operations, can act through all 3 of these mechanisms to increase the throughput of airspace. Advanced CNS may potentially reduce controller and pilot workload as we have more confidence where our aircraft are and the integrity of them flying their routes. They may enable us to reduce separation standards for the same reasons, and also change how we do airspace and route design, as we've seen with some of the RNP or PBN capabilities. So I hope that this little outline of framework will motivate the discussion by our panel and do some good questions among this group. And thank you for your time.
Well, good morning. Really glad to be here. And thanks, Parker, for your analysis. And I'm going to talk about why I totally agree with Parker. It won't work to integrate this into the current air traffic control system. So we're going to have to change things and use a different paradigm for our air mobility. And I think that you've seen this video throughout the week a few times. So I'm just going to play it in the background. And it is our vision of how a seamless urban air mobility trip might occur at the onset. We can keep the sound a little lower, but I think it's fine. So when you look at this, it all seems to be extremely seamless. We're going for an experience that is, you push a button, you get to the vertiport, the aircraft waits right there, you check in very, very seamlessly, you take off and get to your destination without a wait, and land and take another vehicle that takes you to exactly where you want to go. Now, that is exactly what we want to enable, and that's the experience that we're going after. Now, in order to make that happen, obviously, there have to be a lot of things occurring in the background as far as airspace coordination is. And usually most of the traveling public, actually even today, has no idea that while you're flying through the airspace, there's a whole air traffic control system that works between the pilots and the controllers. It's superhuman centered, and while people in the back of an airplane can freely watch DirecTV, surf the internet, or have all kinds of internet connections, pilots don't even have any data connection to the air traffic controller. The current system, they're just talking on a frequency, maximum of maybe 20 aircraft per controller. Is that going to work for us? No, not at all. There's no way. So we're going to have to change things, and we're going to have to address all the challenges that are coming into integrating into the airspace kind of one at a time, and see how we can solve those. And if I want to kind of, here's a list. It's probably not a complete list, but some of the really important challenges that we're going to have to look for. One is obviously airspace access. Parker mentioned this. Just being able to have the room to fly, being able to be controlled, getting into the different kinds of airspace that we want to go, whether it's a controlled or uncontrolled one. Communication, whether it's network communication, command and control, those types of things. Controller and pilot workload were mentioned before. Separation and surveillance of the vehicles. These aircraft are going to be flying in areas where current radars won't work, where you need different types of surveillance, potentially between small UASs that you've got to pick up somehow. Security is a big thing. I mean, we're talking about autonomy, we're also talking about networked operations. We want to make sure that you can't hijack an aircraft, that the communications are secure. Skyport capacity was mentioned before too. Just like runways in the current air traffic system, the spots on the ground are very much a limiting factor to throughput that we're going to have to address and work on. These are, for us, multimodal trips. This is not just the air trip. This is not in isolation. This is not a scheduled service in that sense. It's part of an entire trip where you might start out with a car taking you to the skyport, taking you to the next skyport, and then it might connect maybe to a train. It could connect to a hyperloop. It could connect to another car. It could connect to a scheduled aircraft if you're going to an airport and you really want to continue on. So all these things have to be taken into consideration when planning the airspace services, that it becomes a seamless experience and you're not choking at any one of those points. Noise and acceptability, obviously, a big issue. The aircraft have to be quiet. They have to operate at frequencies where they kind of blend in with the background noise if possible, and we don't want to blacken the sky either. We got to come up with creative ways of making these operations acceptable to the public. And there's a much bigger range of vehicle mixes in this airspace than what we see today in scheduled air traffic operations. I want to talk just a little for a moment about the airspace access. And again, the two areas where we're going to be operating is one in controlled airspace within the current air traffic management system, which is a very safe system, a very human-centered system that's regulated in the US by the FAA, and where the FAA provides the air traffic services. But it's also pretty much at capacity as we speak today. There's not, if you take any busy airport at peak demand, you won't be able to fit any more aircraft in there. So given that, we can't say we want to integrate with this airspace. What we want to do is try to do what helicopter routes are doing into airports, what VFR corridors are doing, just at a kind of more defined scale. Carve out corridors, carve out kind of sections of airspace, which is something that the small UASs are already doing. There's an automated authorization today that people can use to fly inside certain areas of Control B airspace. Now these are predefined grid sections, but we can take this a step further and go into very precise corridors and say we're going to segregate the airspace between what the FAA or other ANSPs are going to be providing, and inside our urban air mobility airspace, we're going to manage the fleet kind of at a very different in a very different way than it's happening today. Not human-centered, network-centered. We're going to fly initially under VFR rules, which is important. It's kind of our entry ticket, but we want to go towards autonomy and a much higher throughput eventually, but prove out that we have all the technologies in place to do that while we're flying VFR. And then in uncontrolled airspace, Class G, PK has led the UAS Traffic Management Initiative for several years now, which is a complete new model compared to what we do today. The FAA regulates, industry provides most of the air traffic services through new approaches, through kind of API-based coordination between different industry providers. And we're looking for much, much higher throughput in those areas. Again, and here, I think the air mobility operations are going to be integrated into the same type of construct. That's what we wanted to try to do. So it's not a human-centered system. It's really much more a network-centric, service-oriented system that lives by sharing as much information as needed for all the operators and all the service providers to operate safely. Here's a quick example about the corridors for Dallas-Fort Worth. We see the ILS approaches to the major runways. There's a helicopter route in the middle. We envision that along the green corridor, we could control our own fleet. We're looking at getting to much higher throughput eventually. I mean, think like pearls on a string, think formation flying if necessary, the types of things that go beyond what we have right now. Not when we start initially, but that's our goal, because this is not supposed to be just a kind of a few rich people flying somewhere, but we want to provide a means for many people to get to different places. And again, we're trying to segregate the airspace where our operations inside the controlled airspace area are from the air carrier operations, and we don't want to burden the air carrier operations. We don't want to burden the current air traffic control system with it. So here are just some primary principles that we're going after. First is safe, going with multiple safety layers. There's a layer that lives on the network. There's a layer that lives in the aircraft with additional sensors, and initially there's a pilot in place. Security built in, baked in from the get-go, including threat monitoring and response if necessary. We want to be very predictable, fly along known routes, corridors, and skyports, so that we're not all of a sudden showing up somewhere. These things will have to be coordinated between the air traffic control system, us, and the municipalities. Want to be very cooperative. The flight intent is going to be shared across the network, so everybody can kind of, also the flight ID, so everybody can know where we are flying and plan accordingly. We want to cooperate with other users in the airspace. Again, managing our own separation, managing our own fleet as much as possible to not burden the air traffic control system, and even getting around some of the current constraints that are two-way communication and clearance deliveries with some other creative ways how we might be able to achieve those. It's got to be scalable, and that is why we have to go away from this human-centered approach to much more of an API-based, service-oriented approach. Of course, keeping in mind that there's lots of things that humans can bring to the table, and we got to be able to resolve all the contingencies and the off-nominal cases, because that's ultimately what's going to be driving the scalability more than the nominal operations. And it's got to be super reliable. That's one of the other things. We have to complete pretty much all of the confirmed flights if we want to make this a trusted means of transportation. If people were to drive to a skyport and then when they get there, there's no aircraft, or you lose all your connectivity, it's not going to work. So those are kind of our main principles. Hopefully, if we get it all right, we're getting to the point where it is like push a button, get a flight, and things do work, and we're building up kind of a, like in this rendering, a network that gets you around in urban areas. So thank you.
Thank you very much, PK, and thank you for the invitation to speak here today. So I'm the CEO of Voom Flights by Airbus. And that's quite an important point, because yesterday, as for those of you who were here, you will have heard Matthias lay out a comprehensive vision about what Airbus's plans in urban air mobility. Airbus is long on this space. We are committed to making electric VTOL a reality. We're committed to making autonomy a reality. But we also know that this market is rife with questions that are unanswered. Questions like, how are people going to actually travel in cities? Will people actually travel in cities through the sky? Questions like, what are they going to do when they're in an airplane? Where are they going? How do they want to get there? And so while we believe that this market is real, at Airbus, we manufacture helicopters. And we believe that you can start answering some of these questions today. And that is the goal of Voom. Voom is an experiment on some level, but it's also an attempt to try and create a market today using existing infrastructure so that we can answer some of these questions as we go forward. So Voom is a mobile-optimized web app at the moment where if you land in Sao Paulo, you can book a flight with us, to Tom's vision. You can actually book a flight and fly within 30 minutes. So we operate at multiple pinnacles around the city, so multiple helipads, and all at the 3 major airports in Sao Paulo. So we are learning a lot. So one thing we are learning is that the market is there, and this is a really important point. So today, people are willing to spend money to fly in congested areas. We are learning how much they're willing to pay. We are learning that, particularly in Brazil, people are remarkably price sensitive. And this is great for us because helicopters have historically been designed without much thought to operating cost. But what we are learning is going to influence how we think about vehicle design going forward. We are also learning about how passengers fly. So today, 60% of our passengers fly with luggage. One of the big considerations is how do you get people and luggage to places, right? So a lot of Brazilians, when they go to the international airport, they're on their way to Disney World. When they come home, they have 5 suitcases worth of luggage. Guess what? No helicopter today can transport 3 Brazilians plus 5 suitcases worth of luggage. So you end up, sending the luggage in a car, which is like remarkably inefficient. So these edge cases are actually not edge cases, and they're real considerations today. For Airbus, what we are learning is what the vehicle needs to look like. So these considerations around how big, how far does it need to go, what is the right use case for this vehicle? How do we take the things that we are learning in the market today and apply them to vehicle design going forward? And it's an iterative conversation. So Airbus has been really great about letting us work with a range of vehicles from different OEMs. And we're learning, what are the things that we need to take from these different vehicles and how do we integrate them together in some kind of optimal vehicle configuration? And most importantly, from my perspective, in order to make this a viable business, we really need to bring down the vehicle development and manufacturing costs. We know that amortization of the aircraft is one of the biggest costs for the operators today. And we need to get the total vehicle price down. And so what we're learning is what does that target total operating cost? We're talking about DOC. What does that actually need to be in order for this system to be viable to create a mass market? And that learning flips a lot of the assumptions about the way helicopters and eVTOL aircraft are designed on their heads. So this data that we are collecting is very valuable. So some key takeaways from us. So to the topic of this panel, airspace management is currently a subjective art. And by this, I mean that there are guys sitting in a room in Sao Paulo that are making rules to kind of suit their needs. So today in Sao Paulo, there's a major domestic airport in the city center called Congonhas Airport. Within a 6-kilometer radius, you can only fly 6 helicopters at once. Why? No one knows. Somebody kind of randomly decided 6, that's as much as I can handle. At the end of December, Guarulhos Airport, the major international airport, decided that they didn't want any more IFR helicopter flights. Guess what? The weather in Sao Paulo is really bad. Last Monday, we canceled 21 flights in an hour when the weather rolled in. Okay, that's a problem. We have access to an IFR aircraft, but it can't go to the airport. So this is and no one knows why. Just because IFR, they decided that IFR is less safe than VFR. For what reason? We don't know. And this is what I mean when I say that airspace management currently is a subjective art. How do you get from that to the vision that Tom presented? We don't know. And it's not, and the human equation in all of this is real. Like, the airspace in Sao Paulo is controlled by the military. And they have a very specific objective, which is to keep the people safe. And while we have a number of commercial objectives in this room, how do you marry those two things? And this is an ongoing and iterative dialogue. And in Brazil, the regulator is really forward-thinking. They're really, really excited that we chose Sao Paulo as the first market to launch. And we chose Sao Paulo because there are 400 helipads, the majority on pinnacles. Landing on a pinnacle is hard. It is non-trivial. Like, you got to make sure that everything is working correctly. And so these are the things that we're learning and experimenting with. And then my second point, trust is a non-trivial hurdle. We are partnering with airlines in Sao Paulo to offer the service to their premium customers. One of the CEOs of a major airline hates helicopters because she doesn't think they're safe. That's a problem. So trust with someone who is in aerospace doesn't want to fly in helicopters. Imagine the balance of the people in this market that are scared of flying in a small aircraft. Getting over the psychological hurdle is non-trivial. On the positive side, the good news, passengers are willing to pay. And most excitingly, they're willing to repeat. So we predicted a 10% repeat rate on a kind of lifetime repeat of our passengers. We are way above that, which is phenomenal for us as a service, because as much as Airbus is willing to experiment, they're not willing to lose money indefinitely. So this is valuable for us to know that passengers are willing to repeat. All right, and then my last point about weather being a real buzzkill.
Windows.
There we go. All right. Oh, can you go back up? Yep, sorry. Weather is a real buzzkill. I told you last Monday we canceled 21 flights. That's a bummer. It's a bummer for the people who need to get to the airport because their international flights are leaving in 2 hours, and it takes 3 hours to get there on the ground. And it's a bummer because it doesn't enable us to provide a reliable service. So the panelists here have talked about the importance of weather. I think Rob mentioned it as well. Real consideration, right? Like, bumpy, rocky rides are not pleasant experiences, right? And so helicopters have a problem with bumpy, rocky rides in bad weather. How are we going to control for these things and build vehicles that are robust enough to handle the various weather conditions? And the places we're talking about are not, like Los Angeles, dry all the time. We're talking about markets like Jakarta, where it's monsoon season most of January. We're talking about Bangkok, where the weather is super variable. Brazil, where the fog rolls in the winter, and in the summer it rains. Mexico City, which is hot and high. Guess what? You can't operate most small helicopters in hot and high conditions. So these are real questions. So this non-trivial in terms of vehicle design. So that said, I would like to invite you all to come fly with us in Sao Paulo, get a feel for what it is like. $50 off your first flight if you come fly with us. We are up and running, so please join us in Sao Paulo, and hopefully soon much closer to home.
But just a little bit of background on me. I've been a venture capital investor for about 15 years, and almost all of my work has been around the underlying technologies that support the greater spread of a middle-class lifestyle worldwide. So that has obviously been things in energy. It has been things around the technologies that support the growth of urban areas. We've had a massive increase in global urbanization in the last century, to the point that now I think over half the world's population lives in cities today, whereas in 1900 that was only 15%. And so I have also particularly been focused around transportation and the role that transportation has played in the formation of cities over recorded history. One of the interesting observations that people have made coming out of that is that with respect to travel, humans have always gravitated towards allocating about a 60-minute time budget per day to their daily routine travel, regardless of whether that travel was long ago restricted to foot or horseback, or whether they had access to rail or automobiles today. And so the shape and the makeup of cities, and cities are really about enabling interactions between its citizens, because that's where societal and economic progress comes from. The size and makeup of cities is vastly shaped by the transportation technology that we have at hand. So we have been living in roughly the same transportation fabric for the last century with respect to how we build our cities, at least. We have had automobiles, and we've had rail, and we've had other variations of that in the form of public transportation. In the last few years with software, we've started to find ways to integrate those different modes of transportation together to make them more convenient for people to make use of. But as we walk up to the potential that we're all here talking about with aerial mobility, one of my biggest questions, and I speak to a lot of people outside of this community who are investors, but they're not yet educated on this space. And they ask me, well, what really is the potential for aerial mobility to shape and solve transportation problems? Will we really be able to move a lot of people off of road transportation and into aerial mobility? And that's a question that I have been, I've met many of you in this process, and that I've been really working in my own investigation of this space to try and answer. I think it's one of the first areas where, as an investor, we can go and focus and begin to deploy capital, because this will help us understand the true nature, the realistic nature of the use case of aerial mobility, what we're building towards, what the scale of that is, what the value opportunity is. And so I've been investing to go after what are those gating factors. Obviously, the vehicles themselves and the noise profile of those vehicles is a big gate to societal acceptance. But from a pilot's perspective, and I also fly, from a pilot's perspective, what are the airspace constraints? What are the interactions that other aircraft are going to have with these vehicles? In our current air traffic control system, as many of you know, there's a lot of there's a big human element throughout it. There's a lot of workload on the part of the individual pilots to maintain separation from each other, and there's certainly a lot of workload on the individual air traffic controllers. And so as we think about an airspace system that could scale up to the level where we're making a meaningful contribution to relieving ground traffic congestion with that type of a network, one of the gates will be, how do we introduce an automated system, but introduce one in a way that works with the existing constituent stakeholders in today's system. Because it cannot just be a technology solution on its own that is put forward without the acceptance and without the incorporation of it by the other people that are already a part of this. Another area that I spend a lot of time on is thinking about what really will be the operational throughput of an aerial mobility system. If we think about a lane of highway, it has a peak capacity, the capacity just before the speed of traffic on the highway collapses. And in the US, that peak lane capacity is about 4,000 passengers per hour. So a 6-lane highway is, at peak capacity, moving 24,000 people every hour. When we look at our concepts for aerial mobility, I think that we can see, from a vehicle standpoint and from an operational cost standpoint, we can see a very compelling use case. We can see a lot of demand for this type of a transportation service. But operationally, from vertiport throughput, from required vertiport spacing with respect to the approach airspace around a vertiport and how we fit those together and what type of density we can achieve, how many aircraft we can put through a vertiport in a given amount of time, how many people per hour is this system going to be able to move, and what are those key gates that we can work on from a technology standpoint? Are there software systems? Is there automation that we can bring forward that we can start investing in now in parallel with the vehicles as a community and thinking about this integration? That is a big area of focus for me where I'm spending my time. So from an airspace standpoint, that's where I'd be happy to contribute to the conversation. Thank you.